Welcome back to our DSA series. Today, we're diving deep into sorting algorithms, essential tools for organizing data. Sorting is at the heart of so many operations in computer science, from simple lists to complex databases. Whether you're a beginner or an advanced coder, understanding these algorithms is crucial. Let's explore them all. Sorting algorithms are methods used to arrange data in a specific order, typically ascending or descending. This operation is fundamental for tasks like searching, data analysis, and more. Today, we'll cover all the major sorting algorithms you need to know. Let's start with bubble sort, the simplest of them all. Bubble sort works by repeatedly stepping through the list, comparing adjacent elements, and swapping them if they're in the wrong order. This process continues until no more swaps are needed, meaning the list is sorted. In this C++ code, the outer loop iterates over each element, while the inner loop compares each pair of adjacent elements. If they're in the wrong order, they're swapped. This bubbling process moves the largest unsorted element to its correct position with each pass. Next up is selection sort. This algorithm divides the array into a sorted and unsorted part. It repeatedly selects the smallest element from the unsorted part and swaps it with the leftmost unsorted element, effectively growing the sorted portion. Here, the minindex stores the index of the smallest element found in the unsorted part. The inner loop finds this smallest element, and then the outer loop swaps it with the leftmost unsorted element, moving the boundary of the sorted section one step to the right. Insertion sort is another simple yet intuitive sorting algorithm. It builds the sorted array one element at a time by repeatedly picking the next element and inserting it into its correct position in the already sorted part. In the C++ code, the key is the element to be inserted. The inner while loop shifts elements to the right to make space for the key. Once the correct position is found, the key is inserted and the process repeats for the next element. Now, let's look at merge sort, a more efficient algorithm. Merge sort is a divide and conquer algorithm that splits the array into halves, recursively sorts each half, and then merges the sorted halves back together. Merge sort splits the array using the merge sort function, which recursively sorts each half. The merge function then combines these halves into a single sorted array. This approach ensures a time complexity of O and log n, making merge sort much more efficient than the simpler algorithms. Quicksort is another powerful divide and conquer algorithm. It works by selecting a pivot element and partitioning the array around it. Elements smaller than the pivot go to the left, and those greater go to the right. The algorithm then recursively sorts the partitions. The partition function arranges elements based on the pivot. Quicksort then recursively sorts the partitions. Its average case time complexity is O and log n, though it can degrade to O n squared, in the worst case if the pivot selection is poor. Despite this, quicksort is often the go-to algorithm in practice due to its efficiency. Heap sort is a comparison-based sorting algorithm that leverages a binary heap data structure. It first builds a max heap from the array and then repeatedly extracts the maximum element from the heap, rebuilding the heap each time. The heapify function ensures that the subtree rooted at index I is a max heap. The heap sort function builds the heap and then repeatedly extracts the maximum element, placing it at the end of the array. Heap sort has a time complexity of O and log n and is particularly useful when memory usage needs to be minimized, as it's an in-place algorithm. Counting sort is a non-comparison-based algorithm that's particularly efficient when the range of input values is small. It works by counting the occurrences of each value and then placing each value in its correct position in the output array. In counting sort, the count array stores the frequency of each element. The input array is then traversed, and each element is placed in its correct position in the output array. Finally, the output array is copied back to the original array. Counting sort has a time complexity of O n plus k, where k is the range of the input values. This makes it highly efficient for certain types of data. Radix sort is another non-comparison-based algorithm, particularly useful for sorting integers or strings with fixed lengths. It sorts numbers digit by digit, starting from the least significant digit and moving to the most significant digit. It leverages counting sort as a subroutine. Radix sort processes each digit of the numbers, starting with the least significant digit. The counting sort for radix function is used to sort the numbers based on the current digit. This process is repeated for all digits, resulting in a sorted array. Radix sort has a time complexity of O d multiplied by n plus k, where d is the number of digits and k is the range of digits. Let's compare the time complexities of these sorting algorithms. Bubble sort, selection sort, and insertion sort have time complexities of O n squared, making them less efficient for large datasets. Merge sort, quicksort, and heap sort all have time complexities of O and log n, making them much faster. Counting sort and radix sort have complexities of O n plus k and O d multiplied by n plus k, respectively, making them highly efficient under certain conditions. Sorting algorithms are integral to countless real-world applications, from organizing data in databases to optimizing search algorithms. Merge sort is preferred for its stability. Quicksort is used when average case performance is crucial, and counting sort is ideal when the input range is small. Understanding these algorithms allows you to choose the right one for your specific needs. For instance, merge sort is used in situations where stability is important, meaning equal elements should appear in the same order in the sorted output as they appear in the input. Quicksort is often favored in practice due to its excellent average case performance, despite its potential worst-case time complexity. Heap sort is useful when memory efficiency is critical. Finally, non-comparison sorts like counting sort and radix sort are invaluable when dealing with large datasets with a limited range of values. And that wraps up our deep dive into sorting algorithms in C++. We've covered everything from simple algorithms like bubble sort to more advanced techniques like quicksort and radix sort. Sorting is a foundational skill in computer science, and mastering these algorithms will help you write more efficient and optimized code. If you found this video helpful, give it a thumbs up, subscribe for more DSA content, and hit that notification bell so you don't miss our next video. Thanks for watching, and see you next time.